Everybody here. I'm sharing my screen now. You should be able to see a brief presentation that I'm going to go through quickly, and then we'll get into the demonstration. So as Natalia said, this is the importing data into MCalibration, and we'll talk briefly about manipulating your experimental data in MCalibration as well. An outline of what we're going to go over. I'll give a brief introduction of me, for those of you who are unfamiliar, and a brief introduction into Veris Engineering and what we do. After that, we'll quickly get into the MCalibration demonstration where I'll show you some files, and then we have a Q&A at the end. So please feel free to put any questions into the chat, and we'll answer them at the end as time allows. And hopefully I'll be able to follow up on any questions that you have afterwards if we can't get to them during the Q&A session. So I am Sean Teller. I'm a senior engineer here at Veris Engineering, and I've been here for a few years. I got my PhD in solid mechanics from Brown University, and there I worked on testing material property characterization of very soft bioengineered materials. I have a few areas that I work in here at Veris. I spend a lot of time with our testing and material characterization group, and that involves both running the tests, analyzing the data, and developing new tests and improving our current test methods. There I focus primarily on the high strain rate and impact testing. That's my bread and butter, and that's where I like to focus my time. And then hand in hand in that is the material modeling and material model calibration, as well as finite element simulation. And so that's what I spend most of my time here at Veris doing, and where I have my expertise. For those of you who aren't familiar, Veris has a lot of things that we do for our clients, and these are three of the biggest areas here, and they fit in with what we'll talk about today. So we do spend a lot of our time doing materials testing and characterization. We started this service after we became frustrated with the data that we were getting from other providers, and we decided to start our own testing lab. There we do focus on your standard tests, but we usually try to focus on providing the most amount of data and information we can in the least amount of tests. We like to call that smart testing, and for those of you who have worked with us before, we think you can see a lot of benefit from fewer tests to get you the most amount of data. Naturally, from that testing, we'll then take the data and we calibrate the material models for finite element simulation. We do that with MCalibration, and we'll do that for most major finite element programs. And then on the right, we'll then take that test data and that material model calibration, and from there, we'll do some sort of analysis. A lot of time that ends up being simulation, whether that's finite element simulation or a CFD type simulation. We also do failure analysis for some of our clients. Sometimes that goes hand in hand with the analysis. We also have experts in material science, electromechanical machines, and semiconductors and processing. So if you have any questions on any of the services we offer, please feel free to reach out to us. As I mentioned previously, we do a lot of simulation here at Veris. This is a brief listing of the software that we use. We have most major finite element packages, including LS-DYNA, Abacus, ANSYS, COMSOL, and the MSC products. We do CFD simulation as well, so we have Star CCM for that. And then we have our own two pieces of software, PolyUMod and MCalibration. And one last thing before we get into MCalibration and importing and manipulating data, we'd be remiss if we didn't talk about testing. Obviously, all this data that we're going to be using here is test data that we've generated on a couple different types of materials. And getting the test data that you need and the test data that is appropriate for your material model calibration and simulation is extremely important. And we've spent a lot of time making sure that we can provide the correct testing services and the best testing services so that data can be the most useful to you and our clients. So we have a lot of different test methods that we do in our lab, and so we've listed some here. We have a lot of different modes. You know, a lot of testing is done either in uniaxial tension or compression, and so you'll see a lot of data from that today. But you can also do testing for simple shear or plain strain or bulk modulus testing. Again, today the data we're going to be looking at is all at room temperature, but many materials, particularly polymers, can have some extreme temperature dependence. And there are some common materials that have a glass transition temperature near room temperature. And so you can have drastically different behavior if you go on the other side of that glass transition. So if your application involves temperature changes, that's something you really need to take into account. Another thing we do is digital image correlation. And if you're not familiar, there's an image on the lower right. That's a full field strain measurement from an experiment that we ran. You know, this can be very useful, especially for polymers where you get into very large strains and very soft materials, and using an extensometer could affect the data itself. So that's a very powerful technique that we use and is well known. In addition to that, we do a lot of impact testing, high strain rate testing, and we also spend a good amount of time doing fatigue and failure testing. This is something we've been doing for the last few years, really getting into. You know, you can do a lot of testing to help you predict failure, as well as just the stress strain response in the material. It takes more data usually. It takes a very careful experimental setup, but it's something that's very valuable that a lot of our clients find. We have some other methods as well, and we also always work and are developing new methods. So if you have questions on anything you might need to do, please let us know. So now I'm going to get into the demonstrations. So you should be able to see my MCalibration screen. We're going to work through a few things, but I'll give a brief introduction to the MCalibration screen that you see when you open it up. On the left here, you should see a few buttons. First one is this welcome screen we're on right now. The next one is called tutorials, has links to PDFs of different tutorials that we put together, and there are a couple of videos linked over on the right as well. The next button is the data tab, or the data button. This is where we'll do data manipulation, and you can also import data. Next button is the main, what I would call the main MCalibration screen. We'll be spending a lot of our time here today as well. This is where you would have your load cases here, your material model here, and these are the stress strain results that you have right here. Then we have some manuals down below. So I'm going to get started. I have over here some data. I'm going to open up the file so we can quickly take a look at it. This is the data file here. There's a little bit of a header which has some information. And we see we have 3 columns that are time, engineering strain, and engineering stress. So the easiest way to bring that data in is I'll grab the file itself and I just drag it into this load case name. And you can see I now have something in my plot here. If I open up this load case, you'll see that it has assumed that my strain type is engineering strain. My stress type is engineering stress, and has also assumed the temperature is at 293 K. Those are correct for the data that I was using. As you saw from the input, it said engineering strain and engineering stress at the top. So I'll hit save. It was already saved, and we can see the data over here on the right. Right now it's showing true stress and true strain. I'm going to look at this data in engineering stress and engineering strain by hitting this button right here. Take a look at the data. This is for a PTFE material, or Teflon as it's commonly called. You can see here the data looks pretty good, as we would expect for PTFE. There's a little bit of noise in the data here, so we're going to take a look at that. I'm going to right click on the load case, and then I'm going to come down to edit experimental data. As you can see, this brought me over here to the data tab, and we can see where we're going to be spending a lot of our time today. This is the data that we've imported, and here's a graph. And then down here on the lower right, we can change what we're plotting. So I'm going to change over in the y-axis to engineering stress and engineering strain. So in this view, we can see each data point is represented by a point here, and then there's a line in between. Now this data here is a little noisy, and I might want to talk to the person who gave me this data as to why it's so noisy and see if I can understand why. But for right now, I'm just going to use that to illustrate some smoothing that we can do. I'm going to select the entire column of engineering stress here, and then I'm going to go to this button, Smooth Data. A dialog will pop up, and what this will do, it will just do a small central moving average of the points. I'm going to use the default of 5 and hit OK. And you can see it got rid of some of that noise. Now, if that significantly changed my data or did something I didn't want, I can always come back here and hit the undo button. I'm going to do that again, and I'm just going to go to a slightly larger average size. Smooths it out even more. One thing to remember, once you're done manipulating data, you always need to hit Save Data to Load Case. So that was a pretty simple example, just showing one load case. The next thing I'm going to do is show you a feature that not many people might be aware of. So I'm going to add a new load case, and I'm going to do that by hitting this plus button right up here. And it brings up the load case setup dialog box. I'm going to hit this button, Load Experimental File. And this is opened up in the folder that I want it to. And I'm going to grab this file here called PTFE Cyclic Tension Transverse Strain. And we're going to open that. This is the dialog box that shows us some information about the file. So you can see here that there are 2,000 rows of data in the file. There's a button here that says View Data Files. This opens a text editor. I'm going to make the box just a little bit bigger. Opens up a text editor that shows you the data itself. So similar to the last one, you can see we have some header here which gives some information on the test. And now you can see that there are 4 columns. There's a time, engineering strain, engineering stress, and transverse engineering strain column. So this is some data that we've taken using digital image correlation, and we've measured the strain in both the direction that we're pulling the specimen and transverse to that. So we can get some information on the Poisson's ratio. So I'm going to hit save, and that transverse strain is really what I want to focus on here. And you can see down here there's a box that says transverse strain column. So I'm going to click that, and I can set the column. It's already set to 4 for me, and we can hit OK. Before I move on, I want to highlight that there's a temperature column here as well. So if you did a test where the temperature changed during the test, you can import that data as well, and that can be used in the calibration. In this example, we just have the transverse strain, so I'm going to hit OK. Again, you can see that we have engineering strain and engineering stress here chosen as our type. Now, if I come in, you can see I have this extra one. I'm gonna turn off the old data by clicking this off button, just so we have the one. So if we look, we have the engineering stress versus engineering strain. You might ask where we can see that transverse strain data. So I'm gonna change the y-axis by going up to this button right here. So I'll hit Y. We can look at that strain by looking at choosing engineering strain, E22, and hit OK. So we can see the engineering strain starts at 0, and then as we get to higher strains, we start to go further and further down. Another interesting thing we can do is we can click this y-axis button and then click on Poisson's ratio engineering and hit OK. You can see here that MCalibration will calculate Poisson's ratio for us based on the transverse strain. In general, we found that the Poisson's ratio is noisier than the other data, and that's due to the fact that typically you're measuring very small strains in the transverse direction, and so there's a little more error, especially at those small strains. You can see that this one starts at around maybe 0.25 or 0.3, and then quickly goes all the way over to about 0.4. And this is engineering Poisson's ratio. You can also plot the true Poisson's ratio. You can see that one gets closer to 0.5 as we get to larger strains. Just like the other load case, we can edit this one. I've highlighted the load case. I'm going to hit Control W on my keyboard, and that brings us to the Data tab. So we could come in here and edit just like we did before, including the transverse engineering strain. And you can see that there's just another column here. I'll go back to the calibrate. I'm going to quickly save this file and bring the data up one more time. So I'm going to close out of MCal, start over with a new file. So we've gone through 2 basic tension tests and how we can use that data. And the data files that we started with were really well formatted. They had the 3 columns we needed, exactly how we needed. I'm going to show you some data that came straight from one of our test machines and how you can manipulate that to give yourself clean experimental data. So again, I'm going to add a load case by hitting this plus button up here. I'm going to go load experimental file. And for this one, I'm going to use the this polycarbonate compression data to low strain rate. I'm going to click this View Data File button, again, like we did last time. And you can see here we have a lot more data. It's ugly. It's got some not a numbers in here. It's really, really messy. You can also see that we have a lot more columns than we did before. In this case, we're going to be interested in time, load, and axial strain. So that's columns 1, 2, and 4. So we need to set those columns accurately here. The strain column, if you remember, was column 4. And I'll show you what we're going to do with this. But we had the load column, but not stress. So we're going to change that to 2. I'm going to call it the stress column for now, but we need to remember that that is load. We'll hit OK, and we'll hit Save. You can see here the data is even weirder than we originally thought. We have a positive stress for a negative strain. That's backwards. So we have some editing to do. So I'm going to go into Edit Experimental Data. Now we've got these 3 columns. The first couple things we want to do, MCal expects the data to start at 0 time, 0 strain, and 0 stress. You can see 2 of the 3 columns don't start there. So first I'm going to highlight the time column and hit this Make Column Start from 0 button. That just subtracts the initial value. So we fixed that column. We'll get to the strain again in a second. Now the next thing we want to look at is the stress. First, the stress is positive, and for compressive stress, it should be negative. So we're going to highlight that. We hit this Multiply or Add Cells button, and it brings up a dialog where we can manipulate the data. I'm just going to put in -1 and hit OK, and you can see it multiplied everything by -1. Next, if you remember, this was the force, and it was the force in newtons. I want the stress in megapascals. So again, I'm going to hit Multiply or Add Cells. And what I'll do here is I'm actually going to put in 1 divided by 32.24. 32.24 was is the area, cross-sectional area of the cylinder we use. You can see here that we can just use divided by. MCal is smart enough to figure that out. So I'll hit OK, and you can see the stress dropped down from that value, and we're now down to something that is probably in the right ballpark. I'm going to save the data for right now. The next thing we need to do is fix the engineering strain column, and there are 2 issues with it. The first is we have a non-zero starting value. We could do that by Make Column Start from 0, but the other issue is we have a lot of toe in. You can see that something in this test was a little off. Either the sample wasn't quite square or something else. We have a lot of toe in we want to correct. So I'm going to show you the way to do that. The easiest way is you can right-click anywhere on the data. There's a toe in compensate first point button. You'll hit that, and then you'll see barely any change here. That's because we have a lot of data points. So for brevity, I'm going to take a shortcut. I just zoomed in on an area of the curve, and then I'll come in here, and I clicked on a data point. You can see it highlighted in red there, and then it shows me that row. I'm going to go from that row. I'm going to go highlight all the way except for the first one, and I'm going to right-click and remove these rows from the experimental data. Now I've got this big ugly jump, and it's not straight. But if I now come in and do tone compensate first point, we get, and a few more times, we get something that looks a lot better and gives me a very nice linear range. Fairly linear range. There is a little more we should probably get rid of. I'm just going to repeat the same thing. That's a lot better. The next thing we can do, this has a lot of data points. There are 6,255 up here. I'm going to hit this button, change number of data points. I'm going to change it down to 1,500. You can see there that's still plenty of data points. That just makes it a little easier, the file easier to deal with. So I hit save data to load case, and I'll go back to calibrate. And now we've got the data in. We went from a really messy data file, and now we have one that works well. I have just a couple more minutes left, so I'll quickly go through a couple things that you might want to consider, and you can ask me questions about. If I edit the load case, I'm going to double click right now on the load case name. There are a lot of options that we haven't had a chance to dive into. So here on the loading mode, all the tests we've done have been tension or compression, so they've been uniaxial. You can go into the loading mode, and there are lots of other loading modes that we support. So here's simple shear, and it gives you a little diagram in case you're confused as to what it's trying to tell you by the name. Other things you can do is if you have an anisotropic material, you can put the directionality in. You can do that by putting in the vectors here based on this little pictogram. We've also pre-programmed a few. If you want to pull in the second direction, you can see how the coordinate system changes. Time stepping is for when you're running a calibration. This changes how MCalibration takes time steps when you run through that. This can be very useful if you want to reduce the number of time steps MCalibration takes. Right now, it would take the 1,500. We might know that we only need to take 500 or 1,000, and so we can change that number, and that'll make our simulations run a lot quicker when we're doing the calibration. Another thing we can do is we can change the plot style. We can change the color of the line. We could add little markers. We can change the line to a dot. So we'll hit save here so we can see it. Those dots are pretty large, or those X's are pretty large, and so they cover everything up. But you can play around with that as you like. The last we can get into is the miscellaneous. This little checkbox here will either add or remove the load case from the legend. So if we hit save, we now no longer have the legend. So that is all I have for you today. I'm going to save this file. That is all I have for you today, going over the data, importing data and manipulating data. And so now I'm going to take a look at some questions. I saw a couple have popped up. Another thing to keep in mind before, if you're about to head out, we're going to be having more of these webinars over the coming months. The next one is scheduled for May 15th, same time, 1 p.m. And I'll be going over inverse calibrations in MCalibration and how you can use that load case. Also, please feel free to reach out to us if you think there are any webinars that you really think that we should touch on. We're looking for more ideas, and we're looking for our users' input into what would be most useful for you for these webinars. So I'm going to take a quick look at the chat, see if there's any questions that anyone has for me. And remember, please feel free to send as many as you need. So we've got a question here asking about engineering strains. I'm trying to summarize. Engineering strains with DIC and how you choose to measure it. How you choose to measure, what area you choose to measure those strains with. If you have a material that shows a lot of necking, like the image that I showed in the PowerPoint. So if we bring that over quickly, so you can see in this image right here, the material necks significantly and the strain localizes. So how do you define the engineering strain for this sample? And that's a very good question. There are multiple ways to do it, but I think there's there are multiple ways to do it, and we've looked at it. We've looked at doing it multiple ways. You can take an average for the entire area, but again, that'll smooth everything out between the areas that are necked and the areas that aren't necked. You can also look at the necking area, and you could put a box here and take an average for that area and an average for that area, and they have the same stress history, but their strain history is very different. So you could try calibrating to both of those at the same time, but you won't get a good calibration between those two. Probably the best way to do it is what's called an inverse calibration. And this is where you create a model in a finite element software of the dog bone itself, and you apply the displacement in the finite element program and calculate the force based on your material model, and then you can compare that. And with a model like that and the appropriate choice of material model, you can get that same necking behavior and then match your experimental data extremely well. So I think that is probably the best way to do it, but it is also the most time-consuming and difficult. And this was a great question, because we're going to be going over inverse calibrations in the next one. So thank you very much for that question. So that's a brief answer to that. If you have any other questions, please let me know. I have, let's see, one more question. It's from asking me to go over the toe and compensation data modification again. Sure. Best way to do this, I'm going to select it, hit Control W. I'm going to change engineering stress and engineering strain. I'm going to zoom in on this beginning area. This is probably not going to be that interesting because we've already toe and compensated. But you just click anywhere on here, right click anywhere on the data, and there's down near the bottom, third from the bottom, there's toe and compensate first point. You click it, and you can actually see that data point disappeared. So if you watch right here, you'll see this data point right here disappears when I do that. Ready? There. What the program is doing is it's taking the data points after that data point, and it's doing a linear extrapolation from those 2 points back to 0 to fix that stress and strain. You don't see the curve move anywhere on this one because all these are already linear because we did this already, but that's what MCalibration is doing in the background. All right, well, that's about it for our time again. I think I'll stay around in the chat room for another 5 or 10 minutes, and if anybody has any questions, please feel free to send them to us, and we'll answer them as we can. Again, we're going to be doing another MCalibration webinar on May 15th that you can sign up on our website, and we're looking for ideas for more. So if you have any burning questions about MCalibration or PolyUMod, please give us the feedback and we'll be able to help you, and we might be able to put together a webinar based on your specific request. So thank you very much. Thank you for listening to me, and hopefully I'll get to talk to you soon. Goodbye.